So today we're going to talk about Euler's method. This is pronounced Euler's, not Euler's. And so just to look back at what we talked about yesterday, we talked about slope fields, being able to draw slope fields or also match a slope field to either a differential equation or the particular solution. And then we can find particular solutions. Remember, particular solutions are just the actual f of x, and you find the plus c. So the particular solution to the differential equation, we can do that given initial conditions. We actually did that earlier in the year. We got a little taste of it finishing up that packet last night. And then we can verify solutions, like does our slope field match the solution that we got? So today we're going to use Euler's method to approximate solutions of differential equations. So we've already kind of looked at a graphical approach to finding solutions of differential equations. That's slope fields. And the analytical approach to finding solutions is integrate, separate, celebrate. So we would consider Euler's method to be kind of like a numerical approach. And basically, Euler's method is just repeated tangent lines. So yesterday, one of the first things that we did in our examples after slope fields was find an equation of a tangent line and use that tangent line equation to approximate some value of f of x. So in this picture down here, and I couldn't erase all of these marks, so sorry about that. In this picture out here, let's say I have this f of x, and I created a tangent line equation that goes through this point, whatever this 0, y point is. So sketching a tangent line. That's the tangent line. And I want to use that tangent line to approximate right here. What is f of 30? Well, f of 30, according to the tangent line, is about right here. That's about equal to f of 30. But I can see that it's pretty far off, right? It's an underestimate because f of x is concave up. And it looks, I don't have any scale here, but it looks to be quite a bit off from what the actual value is. So this would be considered one step in Euler's method. One step of 30 because I went from 0, the point of tangency, to 30, which is what I was trying to approximate. One step of 30. What if instead of one big step of 30, what if instead I make 2 steps to get out to 30? What if I make 2 steps of 15? So let's just mark off where 15 would be. What that means is draw the same tangent line, but stop that tangent line when you get to this 15 mark, which I guess I'm going to scooch mine over a little bit so it matches up with what I have drawn in. Okay, so let's just draw like a little, so we'll do our tangent line, which looks to be about there, but I'm going to stop it right here. There's one step of 30. Now I'm still trying to approximate f of 30, but I want to sort of like change my bearing, basically. Think of this as like if we're flying a plane or something. I don't want to keep going on this path because I'm straying pretty far off. So what if I readjust? At f of 15, what if I find f prime of 15 and come up with a new tangent slope and then use that tangent slope to get myself a little bit closer to what f of 30 actually is. So it's like you're changing your bearing just slightly, alter your course a little bit so that you get there a bit, you're at least closer than you were before. Okay, so 2 steps of 30, that still is just an approximation for f of 30, 2 steps of 15, I mean, but it's better. Okay, so the more steps, the better, right? If I were to divide that into 4 parts, like, what would that be? Steps of 7.5, I guess. If I do 4 steps, and each step is smaller, it's going to be even better, right? So I'm going to say, okay, let's do a tangent. We'll go on this tangent course until we hit 7.5. And then let's take the slope at 7.5 and use that to kind of change course. And then let's use the slope at 15 and use that to change course again. and then it's hard to sketch in. Let's use the slope at 22.5 and use that to change course again, since all those slopes are getting a little bit steeper. And again, my sketches are pretty rough, but this is our approximation. It's the closest one we have yet, right? So you can imagine if I were to increase the steps and decrease the step size. So as the step size gets smaller, 30 down to 7.5, it gets really small, then I would get pretty close to the function value. A common step size that you'll see, like they'll give you a step size on the AP test. A common step size is for delta x, because we're talking about changes in x every time, usually about 1/10 or 0.1, but that can vary. And if they don't come right out and tell you a step size, they'll give you information to find a step size. So instead of just sketching this, we can actually use equations. I was kind of starting to write it out. If I have an equation for f of x, I can figure out f prime at these different values. So every time I come up with a new y value or a new equation for a new y, basically every time I get a new segment, right? It's based off of the old y value plus the slope at the old y times the step size. Let's look at that. So let's see if that's true for, I'm just going to use my middle example because it's easier to look at. So this new equation right here, started at an old y value, and I had a step size of 15, and I used the slope at the old y to get to this y value, right? So I started with an old y. I used the old y slope to get over there, and my step size was 15. So my first little segment was built off of that. And then this segment would be built off of a new slope, the slope at 15 instead of the slope at the previous value. It's confusing until you get some numbers. So, okay, so I rewrote that over here. So find the equation of the line tangent to f of x, given that f prime of x equals x plus y. So that's dy dx, right? F prime of x, just like we had yesterday. Dy dx is x plus y. And the equation of the line tangent has to contain the point -1, 3. Okay, so to write a tangent line, we need a point, which we have, and we need the slope at that point. So dy dx evaluated at -1, 3 is -1 plus 3, so that's 2. So that would be y minus 3 equals 2 times x plus 1. And it might be helpful because we're going to be plugging values in. Go ahead and solve for y. So 2 times x plus 1 plus 3. So far, this would be our original tangent line. Use that to approximate f of -1.1. So let's see. That would be 2 times -1.1 plus 1 plus 3. That's 2 times -1/10 or -0.1 plus 3. That's -0.2 plus 3, which is 2.8. Is this approximation too big or too small? And explain. Well, we need to know about the second derivative to be able to tell if this is too big or too small. And right now we just have an equation for the first derivative. So if I want to find the equation for the second derivative of y with respect to x, remember it's been a while since we did this. We're taking the derivative of x, which is 1, with respect to x. We're taking the derivative of y, which is 1, with respect to x. So plus 1 times dy dx. We're having to do this. And then we sub in the equation we have for dy dx. 1 plus dy dx is 1 plus x plus y. And so finally, the second derivative evaluated at our point of interest, which is -1, 3. I want to see what sign that comes out to be so I can tell if we're concave up or down. So 1 minus 1 plus 3 is 3. which is greater than 0. So since the second derivative, you could also use f double prime, is greater than 0 at negative 1, 3, f of x is concave up. The approximation is an underestimate. All right, so that was an approximation, not using this new method yet. This is just use one tangent line to approximate a value. So now let's use Euler's method. It says start at x equals negative 1, which is the point that we plugged in, right? Sorry, negative 1, with 2 steps of equal size, to approximate negative 1.2. So here's how you do this. First thing to do is figure out what is your step size. What is delta x? So we want to go from our approximation to our starting x value. And since these are negatives, I guess it doesn't matter, but I'm going to write it as negative 1.2 minus negative 1. Like how many units are between those two values? And then I want to divide that by the number of steps, which is 2. So it's always going to be the difference between your starting point and where you want to get to, what you want to approximate, divided by the number of steps. So now this is negative 0.2 divided by 2, so negative 0.1. And we're supposed to start, it says start at x equals negative 1, but I know more information about that. I know that that's the point negative 1, 3. And so what I need to, and the other thing that I need is the slope at negative 1, 3. So I think we already found that in the previous problem. The slope at, oh no, sorry, I won't find that yet. We did find that in a previous problem. Before I get that far, let's build Euler's method. So at the top of the page, I wrote this. New y equals old y plus slope at old y times step size. So what's this new y that I'm talking about? We're starting at negative 1, and we're going 1 step. So our new y will be negative 1 minus a step of 0.1 will be negative 1.1. So you're halfway there, right, if you take 1 step. The new y is equal to the old y, so f of negative 1, the starting point, plus the slope at the old y, f prime of negative 1, times the step size, which is negative 0.1. And the negative matters, right? So make sure if that step is negative, you keep it negative because we're stepping to the left. So what is our approximation for f of negative 1.1? All right, well, let's see. This is f of negative 1 was 3, right? We were given that. And the slope at negative 1, I think we found it up here. The slope of negative 1 was 2 times negative 0.1. And remember, this is what we got for our first approximation anyway. That came out to 2.8. Move this down on the same line so it makes sense. There we go. Okay, that's not the approximation I want, but if I take one more step size to the left, another step of negative 0.01, that will land me at negative 1.1. So my new y is equal to my old y, f of negative 1.1, because now I'm there, right? And let's see, sorry, and I want to do the slope at negative 1.1 times the same step size. So now you were at 2.8. What's the slope at negative 1.1? I don't know. That's what I was starting to find over here, but got ahead of myself. So what is the slope at negative 1.1? Well, remember, the ordered pair is negative 1.1, 2.8. And the formula for dy dx is just x plus y. So negative 1.1 plus 2.8 is 1.7 times negative 0.1. All right, and that's what? 2.8 minus 0.17. So that'll be 2.80 minus 1763, 2.63. So our approximation for f of negative 1.2 on Euler's method is 2.63. That was with 2 steps, right? So again, if you're having trouble visualizing this, you're just saying, we started at negative 1 and we did a little tangent segment to figure out like, okay, where am I right here? So what's the equation for this line and what is that y value? Once you get that y value, you say, okay, start at this y value and now go up a new slope and figure out where you land here. Wherever you land here is your answer after the second step for that approximation. All right, what about this example? G prime of x, y values are provided below. Use this information and Euler's method with 3 steps to approximate G of 2.6. So they're giving us the derivative values at different ordered pairs. So these are x values, obviously, and then these are the y values. So that we don't have to, we don't have an equation for G of x to take a derivative of. All right, so I'm noticing that they started at 2. Started at x equals 2, and I want to get to 2.6. So the first thing I need to do is figure out delta x. So the approximation is 2.6 minus where I'm starting, 2, divided by 3 steps. 0.6 divided by 3 is 0.2. So our step size for this problem is 0.2. And then we are starting at 2, negative 1, because the first derivative was taken at that point. All right, so the first thing I do is say, if I'm going to take a step of 0.2 from 2, my first approximation will be g of 2.2. Trying to figure that out. It will be whatever g of 2 is, plus the derivative of g at 2, times the step size, 0.2. Okay, so what is g of 2? I'm going to write below. What is g of 2? They're showing us right here. G of 2 is equal to negative 1. What's the slope of the first derivative? What's the slope at 2? 4 times 0.2, right? So g of 2.2 is, we're saying, is equal to negative 1 times, 0.8. So negative 1 plus 0.8 is negative 0.2. That took a lot of mental math. It's 6:45. All right. So now what do? We take another step. If I take another step of 0.2, I will be at g of 2.4. All right, so that means that you're jumping off from this point. So you're going to start at g of 2.2, add to that from the derivative of 2.2 times the step size, 0.2. G of 2.2 was negative 0.2. The derivative at 2.2, right there, that's 2 times 0.2. Negative 0.2 plus 0.4 is 0.2. So we're saying g of, you don't have to write this down every time. I'm just kind of trying to do this to organize the notes. So now g of 2.4 is at 0.2. One more step. It says take 3 steps, so I should have 3 sets of work here. So finally, if I take another step of 0.2, I'm at 2.6. G of 2.6 should be g of 2.4, that's my jumping off point, plus the slope at 2.4 times the step size, 0.2. From the previous problem, that was 0.2, plus the slope at 2.4. Ooh, the slope at 2.4 was 0. That's nice to see. So g of 2.6 is equal to 0.2. That's our approximation. All right. Now, did we use this? No, we didn't need this because we didn't have to take it out to 2.8. This is not a previous slope. When you're making an approximation, all the data that you're plugging in and on this side of the equation is from the step before, not the current step. So that's just there to kind of throw you off. All right. Oh, that was our last problem. So we're going to do some AP practice on, I guess, tomorrow. So I have some AP practice, but we also have some new notes for tomorrow too. There's one more day of notes talking about the logistic model. But before we get there, we have tonight's homework, which I believe is number 28. And so how much work do you have to show for these? You really should show basically everything I'm showing here, except for you don't necessarily have to keep rewriting this part. But you really should show these pieces, the equations built, because that's kind of justifying your work. So you could see this on free response, and you wouldn't just want to be doing all of this. I don't know if it'll be calculator or not, but you wouldn't want to just be doing all of it on your calculator and just putting answers out there because you wouldn't get full credit. So make sure that you're showing your work. All right, that's it for today.